Section 5.9, we're going to look at one last component of integration, extend our definition just a little bit. For those of you, I know Kendra and I've had a conversation of sort of like where does this class lead to if you were interested in taking more calculus or whatever. This is actually the very last section of what we do in Calc 1 in the traditional calculus class as well, is this component of information. So it ends at actually the same place. Some of the stuff we do along the way is a little bit different, but it ends with the same kinds of antiderivatives. So we're going to look at some very specific ways to deal with composite functions or products, okay? So our first one we're going to look at is called integration by substitution. There's no integration by substitution on this quiz that you're having on Thursday, okay? So this component of it's not why I said let's wait till Thursday. Integration by substitution says if you have a function f of x, and you can somehow separate it out so that it looks like, if you'll take a look here, this looks like a product, right? It looks like g of u of x, and then you've got this u prime of x, and you can somehow make it look like a product, or maybe it already looks like a product, that this idea of doing a substitution might be useful. So a couple of things that give you clues as to when substitution is useful. Number one, it looks like a product. Okay? So if you've got something that looks like a product, you may have a good candidate for substitution. The second thing is that you usually see something that's inside of something else. Think about chain rule kind of stuff we did before. So when you have a function that's inside of another function, that's another indication that it's a good candidate to use substitution for. All right? And I'm going to show you an example, because once you see an example with those components, it's easier to see how it works. So if you take a look at this particular one, you have a rule that allows you to do this without substitution. But I want to show you how it could be used with substitution so you can see how substitution works. Okay? Do you see a place where it looks like that something is inside of something else? Where are the parentheses that are sort of not visible on your paper right now? Around the exponent. Okay? If you were putting this in your calculator would force there to be parentheses here. It would. Most calculators would anyway. I have one that doesn't, but most of yours do. It would put parentheses there sort of automatically for you. Okay, the part that it looks like is in parentheses is going to be what we identify as u. This is going to be called u substitution, and there's nothing special about the letter u. I don't know why u is used, so I can't answer that question. But u is the standard substitution letter here. And it's going to be that part that's in parentheses. All right, so we've got u is equal to 2x. What we're going to do next is we're going to actually take the derivative of u, so du dx. What is the derivative? And I know that looks funny because we don't usually use that notation, but I'll show you why in a minute we're using it, so just bear with me. What is the derivative of 2x? Not antiderivative, derivative. 2. And I'm going to take this equation and I'm going to rewrite it with du on the left. So in some sense, I'm sort of multiplying the dx to the other side. That's not exactly what's going on, but we're just going to pretend notationally it looks a lot like it, that we end up with this. Okay? Du is equal to 2x. Sorry, 2dx. Now most of the time, after you've done a few of these, what you're going to see, that wasn't what I meant to do, let's get this one, is these two written down. Most people don't write the du dx equals to 2. They write du equals 2dx. That's just what they write second. All right, so what we're going to do with that information is we're going to come back to our original function over here, and we're going to rewrite this function with replacement. So we're going to substitute in the pieces that identify what's there. Now notice there is no e in my du and u and stuff over here, so e is going to still be there. Now, the exponent was originally 2x, and I have identified that 2x has sort of a new name. Its new name is what? U. So I'm going to rewrite this so that the exponent is now u instead of 2x. I also have another replacement I can make. The 2, which is at the beginning, and the dx that's at the end, when they're put together, they're equivalent to what? Du. So I'm going to replace those two components with the du at the back. And once I've done my replacements, my substitutions, I'm going to integrate or do antiderivatives just like normal. What is the antiderivative of e to the u? e to the u and plus c. Somebody said it. Plus c. Now, if you stop this problem and give me this as your answer, you have forgotten something. Any idea what you might have forgotten? Some notation. There's a notation issue. I don't have any numbers in this one. I mean, there are some numbers that are going to show back up. You could say I might have forgotten the notation at the beginning. That's not the notation that's got the problem. What was it over here you guys said? F of u, same thing as what Kendra was saying. We could write that down. That's not the notation that's a problem in this problem, though. That's what you have to do. The original problem started out with x in it, didn't it? So your answer needs to be in terms of x. Whatever the variable is when you begin the problem, that has to be the variable at the end of the problem. So we're going to do some sort of like a back substituting step. What was u? 2x? That doesn't look good. Let's try that again. This is equal to this. You can give it a name, capital F of x, if you'd like. It wasn't actually called lowercase f of x to start with, so you don't necessarily have to. Dakota.
What happened to 2 in front of the e?
The 2, they're circled. Let me do it in a different color. This 2 and this dx were replaced over here with du. I took the 2 and I took the dx and I replaced them with du. That's where it went. We're going to do some more examples with this in a minute, but I want to show you one more method, and this second method I'm going to show you is the one I wanted to make sure you saw before Thursday's quiz, okay? It's called algebraic manipulation. The idea is to simplify something with algebra in order to use basic rules or substitutions. It's not a calculus thing. It's algebra. That's all it is. So it's going to be simplifying something using algebra. So potentially it could be something where you're like foiling something out. I saw a student teacher this morning teach foiling to his pre-algebra students, right? First, outer, inner, last, distribution, whatever. It could be that. The example I'm going to do is a little bit different than that because usually the foiling thing, when somebody sees it, they recognize, oh, I should simplify this to start. But my example that I'm going to do with you is not one that everybody always sees of what they should do to start. You guys ready to see an example? This problem looks like division, doesn't it? But it's division with a single term. We call a single term a monomial on bottom. The reason that that matters is because I can actually separate this out so that each of the components of the numerator is written over the entire denominator. And the reason that's useful here is because the entire denominator is one single expression. So if I take a look at this from this perspective, what is x squared divided by x squared? It's 1. So I have yet to do any calculus. Everything I'm doing right now is algebra simplification. How else could I write 1 over x squared to be easier to work with for our calculus that we're about to do? X to the negative 2. Algebraic manipulation is simply the idea of simplifying the algebra into an expression that allows you to use the calculus in an easier way. Okay? Now that we're at this point, we can actually do an antiderivative. What is an antiderivative, or what is the antiderivative of the number 1? It's just x. What is the antiderivative of x to the negative 2? Divided by negative 1. Right? Increase the exponent by 1, so negative 2 plus 1 is negative 1. Divide by the new exponent, negative 1, plus c. Good job. And for the purposes of everything we're doing, you can leave it like that. If you really don't want to leave it as x to the negative 1, you want to put the x back in the denominator, you can do that, but you don't have to. It's fine as is. Okay? Algebraic manipulation. All right, so we are going to take a look at 4 examples. The examples that we're going to look at next, also, the very end of each of them aren't going to be what you see on the quiz, because what you see on these is you see numbers at the top and bottom. These are called definite integrals. We're going to plug numbers in, all that good stuff. So that part is not going to be on your quiz, okay? The gateway does not include any of that. But everything that we do up to that point is things, or are things that could be showing up on your gateway, okay? Just not the plugging in the numbers. So the directions say find the exact value of the integral by using antiderivative formulas if possible. If that's not possible, then use technology to estimate the answer. In either case, state whether your answer is exact or an approximation. Okay? So our first one has the integral from 1 to 4 of natural log of x dx. So the first question you have to ask yourself is, do I have a way to find an antiderivative of this function? This function's natural log x. Do you know an antiderivative for the natural log of x? Mm-mm. 1 over x is the derivative, but we want the antiderivative. Nope. If you were to go back to 5455, where we wrote down all of our list of rules, what you will not find is you will not find an antiderivative form for the natural log of x. It's just not there. Okay? It requires something called integration by parts. Integration by parts is a calculus 2 concept to actually find the antiderivative of this. It is not something people do in Calc 1. You just don't. It's an advanced technique of integration. So right now, you don't have a technique to do this. You've not learned one. So this is one of those cases where it says, use technology to estimate the answer, because you do not have the ability to do that. So if you want right now, you can already write down that you're finding an estimate. You are not going to find an exact answer, okay? And we're going to let our calculator do this for us, and we just learned how to do that, didn't we? Oh, yes, we did. All right, so we're going to take a look at what happens with our calculator to find this. So in y equals in your calculator, change this to say natural log of x. And because it's super fun to see it anyway, we're going to do it in the picture window because, you know, we can. So we're going to hit our graph button. If you want to do zoom 6, that's your standard graph. But it looks something like this. And the paper says, our problem says that we're supposed to go from 1 to 4, right? Okay, so if you'll remember, what we're going to hit is second trace, number 7, lower limit 1, and enter, upper limit 4, and enter. It's going to shade it in, and it's going to tell us the answer along the bottom, and we're going to use 3 decimals of accuracy. So 2.545. Is everybody good with that? So you're like, yes, please give me a whole bunch of ones I don't have rules for, right? Because those problems are going to be your easiest ones to do. H star. All right, let's do the other 3. I think the other 3 are all possible to do. All right, this is an interesting one because I just told you it's possible, but you see a natural log of x in it, don't you? Yeah, and that doesn't really look like I can have said, I'm saying the same thing twice. It sounds like I just contradicted myself, doesn't it? I just told you it's possible, and then you see a natural log, and we just did one with the natural log, and it wasn't possible, so what's the deal? All right, so here's the deal. Do you see how this problem looks like division? Yeah? The other problem we did that looked like division, there was a way to simplify it with algebra, and that was fine. This one doesn't have that, though, because I don't have like a polynomial on top, right? I've got a natural log on top. It's called a transcendental function. I can't just simplify that with algebra, but I can use substitution. So here's how this works. I would like for you to write down that u is equal to the natural log of x. What is the derivative of the natural log of x? 1 over x. Brock told us that earlier. It's 1 over x. Now this should say du on the left, and then we multiply the dx to the other side, so we've got a dx over here as well. Everybody good so far? Here's the cool thing. There is a natural log of x written over there, and there is a 1 over x written over there. And if you don't see it, it's because you're not thinking about the denominator in quite the right way. This is the same as the natural log of x times 1 over x. That's what division by x is. It's the same as multiplication by 1 over x. So in a very real sense, that's what you have over there on your original problem. So the natural log of x, here's the dx at the end. I've still got my integral from 2 to, what was it, 5? Okay, so I'm going to write the integral. Please do not write the 2 and the 5. I'll tell you what to do with them in a minute. Just ignore them for the moment. Natural log of x has a new name. What's its new name? U. Right? I'm replacing this piece. And this piece that says 1 over x dx also has a new name. Its new name is du, right? 1 over x dx has a new name, du. So let me tell you why we're not going to put the 2 and the 5 on there. The 2 and the 5, as they were originally given, were limits of integration for what variable? X. Your problem doesn't have any x's in it anymore, does it? And that 2 and the 5 are not values for you. So we leave them off for the moment. We will put them back on later, but only after we turn them back into x's. Okay? What's the antiderivative of u? U squared over 2. Now, if you were doing this on a test, you'd put the plus c at the end and you'd be done. But this particular problem has numbers that I'm going to have to deal with in a minute, so I don't really need the plus c because it's going to cancel itself out later anyway. So you can leave the plus c off. Now, if you were just doing u substitution in general and you didn't have any numbers, you still couldn't leave it like this because it's in terms of u and it's supposed to be in terms of x. So I need to put it back in terms of x. So what am I going to replace u with? Natural log of x. And again, it looks funny, but make sure your natural log of x is all of it as a whole squared. If you put a squared on natural log of x without those parentheses, it means that you're squaring the x, not the natural log of x. So those parentheses are crucial because it means something different. This is all over 2. And now that it's back in terms of x, I can use the limits of integration I was given, which was 5 and 2. So literally, what we talked about last time is you can take the 5 and you plug it in for x. So this is natural log of 5 squared over 2 minus natural log of 2 quantity squared over 2. And this will give me an expression. It'll still be an approximation because this is going to be irrational. So I'm still going to get an approximate, but let's figure out what this would be. My calculator is going to be able to help me on this. In my regular screen, if I'd like, I can type in and put a parenthesis. Natural log of 5 squared over 2 minus parenthesis natural log of 2, whoa, not tangent. There we go, squared over 2. And I'm getting 1.055. Yeah, that's what I have as well. So a couple of things. We aren't finding average value. We're just finding the actual calculation. So if it asked for average value, you would, but this one didn't ask for that. Yeah. Couple things over here. This piece over here would be an exact value. At the point when you got this, this is rounded, so this is an approximate or an estimate, right? Because we had to stop our decimals. Not approx, approx. Let's try that again. Now, if you wanted to make sure that you got the right answer, and I would encourage you to do it, especially if you're working with even problems, you can do that. Here's how you do that. In your calculator, grab a calculator and put in, was it natural log of x over x, right? In y equals, you can put in the natural log of x divided by x, and you can graph it. And you can make your second trace, number 7. Our lower limit was 2. Our upper limit was 5. And it tells us along the bottom of the screen I have 1.05491, so forth, just like I did a minute ago. Yes, Brock?
And did you say these were going to be on the gateway?
No.
They're not going to be on the gateway?
No.
So on the test, we'll do the test?
Yes. Next Tuesday.
Calculate for all of them?
No.
Have to go through that?
There will be places where the directions say much like this. If you can do it exactly, you should do it exactly. you're welcome to use an approximation to verify your answer. So like what I just did with the calculator would be verifying my answer. And in some sense, you guys do that probably every time you have an odd problem anyway. You flip to the back of the book, right? And nobody asks me when you do that, do I have to write it down because it's already in the back of the book? So it's the same kind of thing, right? Your calculator's verifying your answer for you, much like the back of the book on a problem like this.
Can you do the calculator area thing? Mine said error.
Okay, 2 more examples. Let's check it out. All right. There's no natural logs. Okay, so it's not like, this is all about natural logs. It's definitely not. You do see something that looks like division, right? If you were doing this and you were trying to find a derivative, oftentimes you guys would probably have rewritten this or would rewrite this like this. Let me rewrite it. Right? Take the denominator, pull it up with a -1 exponent. That's what we've been doing when we did derivatives. We use a product rule then, right? That's what you guys did on your first gateway. And we're going to do the same thing when we get to this point for an antiderivative. This does not have algebraic simplification because the denominator has 2 parts to it. There's addition in the denominator. So that's uniquely different than the earlier algebra problem we did. Okay? So that's something to be aware of. However, this can be done with substitution. Do you see how it looks like there's a product, first of all? Do you see a product? Yes. Do you also see a function that looks like it's inside or embedded inside of something else? Yes. The x squared plus 1, right, Matt? Yeah. And that's what we're going to let our u be. Our u value is going to be the part that looks like it's inside of another function. In this case, x squared plus 1. So then, what is the derivative of that function? Derivative, not anti. 2x. And then we put the dx beside it. And do you see back in the original equation the 2x? Yes, you do. So here's our 2x and our dx. Those 2 components of this actually create the du. So if I take the part that's in blue, I can replace the blue parts with du because 2x dx is equivalent to du. Now the part that's in parentheses, x squared plus 1, also got a new name. Its new name is u, right? But the -1 stays put. It's not a part of what u is defined to be. So it's still there. The integral is still there. The 3 and the 4 are still there too, but we don't want to write them down because those are numbers that apply to x, and we just turn things into u. All right, so what is our antiderivative of u to the -1? There's such good thinking skills going on right now. You guys are doing awesome. You are all wrong. That's true. It's not 1. It's not 0. It's not u to the -2 over -2. Hannah was the closest. She said something that was almost on there. Yeah, that's it. This expression also could be written this way. Agreed?
I was gonna say that.
Yeah? U to the -1 is the same thing as 1 over u. I know this should have absolute values, but we're going to be putting positives in there later anyway, so put it there or don't put it there. It's not going to matter. But the antiderivative of 1 over u is the natural log of u. But of course, u is not really our variable. It's sort of this made-up variable that we have created to help us out. It's supposed to say what? X squared plus 1, right? Again, use the absolute values or don't. X squared plus 1 is always a positive quantity. And once we have it back in terms of x's, I can use my numbers, which are 4 and 3. So this actually ends up being the natural log of 4 squared plus 1 minus the natural log of 3 squared plus 1. So what's 4 squared plus 1? 17. And what's 3 squared plus 1? Okay, so this is the natural log of 17 minus the natural log of 10. That's an exact value of this. There's another version of this that you might remember from algebra that you can write this as 17 over 10 like that. If you don't remember that, or if you didn't do natural logs enough to remember that, that's fine. It doesn't matter. Just be aware if you looked at the back of the book, those are the same thing.
I thought they had the same base. Or is that just for one?
Yeah, same base. They do have the same base. They're base E because it's natural log.
7.
No, those aren't the bases. The 17 and the 10 aren't the bases. The base for a natural log is base E. Natural log of x is the same thing as log base E of x. The base is E.
Now, if it's a log and they have the same base, you could.
Yes.
Okay, that's what I was looking
Yes, that's correct. Okay. At any rate, either of these are perfectly legitimate answers. Doesn't matter which one you use. If you want an approximation or a decimal to know what that's approximately equal to, I only have 2 decimals written down for some reason, so let's see what this is. So if we did natural log of 17 minus the natural log of 10, and just to show you that it really works, you can also do 17 divided by 10 like this. So do the same. 0.531. That's the approximation. So this one is the exact up here, and this one is an approximation down here. Are we cool with that? We've got one last example. And it actually already starts out looking like a what? Product. Looks like a product, doesn't it? Oh, I'm not on my screen. I'm sorry. Didn't get it flipped over. Okay, this one already starts out looking like a product, agreed? You could, like, cube this thing out. You could do that. It would be messy and it would take a while. Agreed? Yeah, I don't want to cube anything. If I have to square something, maybe. If I'm going to cube something, that's probably not my first choice. All right? It looks like a product, and it looks like that there's something inside of something else, doesn't it? Those are the red flags for use substitution. Looks like a product, and it looks like something embedded inside of something else. So if that's the case, or if we're going to try use substitution, the u would be the thing that's embedded inside of something else. So what is embedded inside of another function? 1 plus 2 to the x.
I have a question. So,
Yeah.
like on the last problem, the u is like the derivative is always worked out to where it goes back to x. Is it always going to be like that?
No, this one's not going to. I'm going to show you what to do, and it doesn't. Yeah, it doesn't always. Well, you'll see that most of it's here. All right, so let's find the derivative. What is the derivative of the 1? That's 0. What's the derivative of 2 to the x? Good. 2 to the x, natural log of, whoops, not 5. I don't know why I wrote that down, 2. Please remember the dx on the end. Remember, it's really du dx on the left, and then we multiply the dx. Okay. Now, this answers Matt's question right here. Because if you take a look, there's a natural log of 2 here, and there is no natural log of 2 in your particular problem, is there? Now, most of you have encountered a problem where you saw a natural log of 2 on a gateway, and you told me the derivative of natural log of 2 was something that it wasn't. So this isn't the same question I'm dealing with at the moment, but what is the derivative of natural log of 2? 0. Why? Because it's a number, right? It's just a number. There's no variable. With just natural log of 2 by itself, that is a number. It's an ugly decimal approximation if you wanted to use your calculator, but it's just a number. Okay? So really what I have here is I have the 2 to the x, which I need, and I have it multiplied by some random other number. So here's what I'm going to do. I'm going to move the random other number to the other side of my equation. So in a very real sense now I have 2 to the x dx on the right, and I have 1 over the natural log of 2, or you can write it as du over natural log of 2, and then the du there. So here's my 2x and here's the dx. 2x dx is equivalent to 1 over natural log of 2 du. So when I do my replacement now, whoops, okay, that wasn't what I meant to do. Let's try that again. When I do my replacement, I will have the 1 over the natural log of 2, and I will have the du, replacing the part that I just highlighted in blue. The 2x dx gets replaced by 1 over natural log of 2 du. The part in parentheses, 1 plus 2 to the x, what will it be replaced by? U. And that u will still have a negative third exponent, or third, right? Yeah, power 3. There we go. And I still have the integral at the beginning, and I'm not writing my numbers of 2 and 6 until later. I'm going to ignore them for the moment. Okay. 1 over natural log of 2 is a number. It's a constant multiplier. Constant multipliers just come along for the ride, whether it's a derivative or an antiderivative. So my solution here will have 1 over the natural log of 2 in it. U to the third, however, what's the antiderivative of u to the third? U to the fourth over 4. And again, I'd put a plus c if I didn't have limits of integration. I do, so I don't need the plus c. If you'd like, you can write the denominator as 4 natural log of 2. You can't multiply the 4 and the 2. 2 is inside of a log, 4 is not, okay? So I'm putting the 4 at the beginning to specify that. What is u? 1 plus 2 to the x, raised to the power of 4. And it's evaluated from 6 to 2. So far, so good? So I've got 1 over 4 natural log of 2. And I'm going to plug the numbers in. So now I have 1 plus 2 to the 6th to the 4th minus 1 plus 2 squared to the 4th. It's messy, it's ugly, it's simplifiable. You can use your calculator to simplify that, right? You can tell your calculator 2 to the 6th. What is 2 to the 6th? You know? 64 is right. And then I add 1, I've got 65. So in some sort of sense, I have 1 over 4 natural log 2 here. And this is 65 to the 4th minus, what is 2 squared? 4. 4 plus 1 would be 5, and this is 5 to the 4th. And can our calculator do this and give us an approximation? I mean, give us an exact answer to simplify this? It definitely can. So if I did that, just so that you're aware of what it is, it actually ends up being 44,625,00 over the natural log of 2. So 4,462,500 over natural log 2. That's the exact expression. It divided out with the values inside. If I actually simplify 65 to the 4th minus 5 to the 4th, I'll get into numbers divisible by 4.
So, and then we just approximate.
Yeah, so this would be the exact. And then you can get an approximation for this with your calculator. Again, I only have 2 decimals written down for whatever reason, so let's see what it is. I have an approximation of 643,8026. Actually, 0.62 is as far as my calculator would go. I'm running out of decimal places. It won't let me have anything larger on my screen. So this is as good as my calculator can give me on my screen. This would be my approximation. All right, so in terms of Thursday, what of this do you need to be able to do? You don't have to do substitution. No problem on your quiz on Thursday will require you to use substitution. It just won't, okay? However, there might be algebraic manipulation. So as you're looking at what is this, what applies from what I'm looking at in 5.9, it's the algebraic manipulation problems. Things where you're simplifying by dividing or multiplying things out to get your values that you're going to integrate, okay? Other than that, you won't have any of the plugging in numbers. None of those things where we plugged in the 6 and the 2 here, that won't be on there either, all right?